Hello and good morning to all of you. So this is Vijayam Physics classes. I am Siraj Kumar. So today I am standing before you to say about this simple harmonic motion. See, in the last classes we discussed about the simple harmonic motion, the wave equation, and then we discussed about the energy of the simple harmonic oscillator. Apart from that, we discussed about displacement, velocity and acceleration. And see here, we also discussed about what is called the angular SHM and simple pendulum, torsional pendulum and physical pendulum. See, in today's class, we are going to discuss about the spring mass system. Okay, see, what is a spring mass system? See, the spring mass system means what here? Suppose, for example, if I take a smooth surface, this is smooth surface. See here, on this smooth surface, if I take a block of mass m, okay, and here this one is connected to a spring, and the spring is fixed here, and see this one is a mean position. Now here, say from this mean position, suppose if I displace this mass, okay, see if I displace this mass, then see what will happen here. See, it will move to this side. Let us say it has moved to a distance x. Then you see we will have a restoring force this side. This is restoring force. And you see here what is the k here? See, the k is called spring constant. Okay, see here k is called spring constant. So k is a spring constant. And here what is the f here? F is called the restoring force. Okay, and see carefully, then here what you can add, see you can add f is equals to minus kx, or if not, see you can also add f is nothing but mass into acceleration, it's nothing but minus of k into x, or if not you can add here, see acceleration is equals to minus k by m into x. Therefore here what you can add is, see acceleration is equals to minus omega square x regarding SHM, that we already got. Means what, see these two are, if you observe here carefully, so I can write here in the place of k by m, I can write omega square. So therefore here, see what is k by m here, see k by m is nothing but omega square. Therefore here what is the omega here? Omega equal to root over k by m. See here what is omega here? See the omega is nothing but angular frequency. Okay, angular frequency, and it is equals to 2 pi by capital T. See omega is nothing but angular frequency, which is equals to 2 pi by capital T. Okay, then see carefully here, then let us substitute in the place of omega 2 pi by capital T is equals to root of k by m. Therefore what is the time period of this spring mass system? See, it's nothing but 2 pi root m by k. See here what is the time period of a spring mass system? It is nothing but 2 pi root m by k. And here the time period basically depends upon what? See, the time period basically depends on the mass what we attach to this. And also it depends upon the spring constant. So that is the time period here. But here suppose now it is placed on the horizontal surface. Okay, we got this expression. Then suppose if it is hanging, then how you will get the time period? So let us consider the spring here. Suppose this is the spring, and here it is connected to a mass m. This is spring constant k. So when you just keep it and when you just release slowly, then what will happen? See, due to its weight, it just comes down. See here, let us say, see the weight here acting is mg, and here due to this weight, let us say the expansion in this one is x. Say first assume that, say let us say, so here is the mass, now it is extended by x. Means here what you can write here, see here you can write here mg is equals to kx. Okay, say the weight is nothing but equal to kx here. Say let us say this is the equation number 1. Okay, now see observe here, say let us say, now you just expand this one a little bit further. Okay, see let us say the same spring, see what you do, now you expand it. See let me draw another diagram, that will be easy. Okay, see here, let us say the same spring, the mass is attached here. Now it is already expanded. Now it is already expanded by distance x. Now here let us say, now you further extend it by distance x. See x, let us call it as x1. So you further extend it by distance x1 and release. Then what it will do? It will do oscillations. Okay, then let's say when it is doing oscillation, now tell me here what are the forces acting here. One is a restoring force is acting this side, and the next one its weight is acting downward. So therefore here see here, then here say let us say it is accelerating in this direction, let us say. See this is the restoring force F. Okay, minus mg is equals to say k into x plus x1. Can I write like that? Okay, see, sorry, it's nothing but see a mass into acceleration. Can I write like that? See here, that is F here, and this is mg downward, and the acceleration is upward. So definitely F is more in this case. Therefore, you see F minus mg is equals to F minus mg equal to mass into acceleration. But you see here, what is the restoring force here? See here, I am not taking any negative symbols or anything. I am just taking the magnitudes and I am doing this one. Now tell me what is the force here? See, force is nothing but k into x plus x1. Okay, so let us substitute that one here. See here what you get here. See kx plus kx1 minus mg is equal to ma. But see here from the equation one what we got here, mg is equal to kx. Say kx equal to mg means what? See, let us strike these two. Therefore, here what you will get here, see ma is equals to kx1. See here, a is equal to k by m into x1. Therefore, here a is equal to omega square into x1. Means what here? Omega square value is how much here? It is k by m. Therefore, omega equal to root over k by m. Means what here? The time period equal to 2 pi root m by k. Okay, means here if I take a mass and if I take a spring of spring constant k, and when it is allowed to oscillate, see in any case the time period is what? The time period is 2 pi root m by k. Means a time period does not depend upon the acceleration due to gravity. Okay, it is independent of acceleration due to gravity and it mainly depends upon the mass and k. Okay, see, let us continue this one. See, let us say, for example, sir, why sir, like this? So let us take another case. See, let us try another case here. See, here, let us take, you may take in the case of this one. So let us take the angle theta, and you see here also you keep one mass m and keep the spring here of spring constant k. And you just extend it little and release, then it will do oscillations. Okay, and if not, if not, okay, let us take the spring, let us keep the mass m, and in the water or in any liquid, and here also you just extend it and release, then it will do oscillations. Okay, that time you calculate. In any case you take regarding spring mass system, the time period is always 2 pi root m by k. Means what? It is independent of g. Okay, it is independent of the surroundings here. Say for example, let us take a satellite. Say if the satellite is rotating around the earth, then here suppose there I wanted to calculate the time period. Means I wanted to calculate, I want to know the time or the time period. So that time I should not use simple pendulum. See, simple pendulum depends upon g. And if a satellite is rotating around there, its g value will change or maybe 0 in some cases. So therefore here, see time period we must use the spring mass system. So if I go to moon, I need spring mass system, not the simple pendulum. So there the simple pendulum is not useful. So this is useful for me. So this is the spring mass system. Okay, so here in the spring mass system, the time period is 2 pi root m by k. In most of in any situation like this, because it is independent of g. Suppose if you just keep little bit like this, then the time period is not this one, that is different. Okay, that we'll discuss later. So in the next video I'll explain about that. Okay. Okay, now see, observe here carefully. Now see, let us discuss more about this single mass oscillations, the time period of this single mass oscillations. Then see here, observe here. Suppose if you look at this K, what is this K here? The K is called spring constant. Okay, see, remember the spring constant basically depends upon the length of the spring. So L is called as the length of the spring. Okay, see here the spring constant basically depends upon what? It depends on the length of the spring. Means what here? More the length of the spring, less the spring constant. More the length of the spring, less the spring constant. Less the length of the spring, more the spring constant. Means what you can write here, see, K into L is equal to constant. Therefore, you can write here K1 L1 is equals to K2 L2. See, for example, let us take one spring of length L and K. Suppose say you make it into three parts. Okay, you make it in three parts. See here, let us say one is L by 3, another one is L by 3, another one is L by 3. But you see, all the three will have different spring constant now. They are not the same like K. So let us substitute here. See, K1 L1 is equals to, means K1 means K, L1 is L here, and here what is K2 that we have to find, and L2 is L by 3. Therefore, see, what is the K2 value? It became 3K. Means here, see, the spring constant basically depends upon what? It depends upon the length of the spring. Okay, if the length of the spring is short, then the spring constant value increases. Okay, so this is one important point. Okay, then see, let us discuss about the springs in series. Springs in series. So what do you mean by springs in series? Means what here, if the spring is connected one end to the other, then that is called as springs in series. See here, let us say this one is K1, this one is K2. Or if not either like this. Either, see, this is K1, this is K2, and this is the mass. See here, in either case it will be same. But here, remember, when you say something is in series, if they are connected one end to the other. Now suppose let us say I applied force in this direction. See here, when I applied force in this direction, then what will happen? There will be restoring force in opposite direction. Okay. Now here in this case here, see as the spring constants are different here, then here this one will expand by distance x2. And in this one will expand by distance x1. So different extensions will be there. Therefore now tell me here, what is the total extension here? It is nothing but x is equals to x1 plus x2. Okay, then see, can we see here, what is the restoring force F1? It is nothing but K1 x1. Okay, same force. Remember in the here, see here we are applying same force here. See, force is same, but here the extension is different. So when the springs are in series, the force acting is same. The force acting on the body is same, on the spring is same. So therefore, yes, here F is equal to how much here? See, K1 x1. Therefore, see here, what is x1 here? It is nothing but F by K1. Similarly, F is equals to K2 x2. Therefore, what is x2 here? It is nothing but F by K2. Then you see, this is the total length here. What is this one? See, F is equals to, because same force. See, K in series into x. Therefore, what is x here? It is nothing but F by Ks. See, let us substitute here. See, x is equals to F by K in series. See, Ks means what? K, effective value of K in series. Okay. Therefore, see here, F by Ks is equals to, okay, F by K1 plus F by K2. Okay, therefore here what you can write here, 1 by Ks is equals to 1 by K1 plus 1 by K2. So if there are n springs are there, then what you write here, 1 by Ks is equals to 1 by K1 plus 1 by K2 plus 1 by K2 plus and so on like that. Okay, see here for the n springs. Okay, are you understand? Here in the series, same force is acting, but at different extensions. Now say similarly, let us observe here in the case of parallel. Say in the case of parallel, see what will happen. Okay, see observe here carefully. Say the springs in parallel. Springs in parallel. Okay. See when the springs are in parallel, then see what will happen. See, let us say when you will say the two springs are in parallel. Let us, this is one spring, this is another spring. They are connected to a mass M. So this one is K1, this one is K2. Okay, or see here the diagram may be like this. So this is one spring, or this is another spring which is connected like this. So this is K1, this is K2. And if you observe here carefully here, see here when you just extend this mass, see both will have same extension, but here different restoring force. This is F1 and this one is F2. Okay, therefore here what is the total restoring force here? The total restoring force is nothing but F1 plus F2. That is the total restoring force. And here what is F here? Say F is nothing but see K in parallel into same displacement. And here F1 is equals to K1 into X, same displacement. Therefore F2 is equal to K2 into X. If I substitute here, see K in parallel into X is equals to K1 into X plus K2 into X. So therefore what is the K in parallel here? It is nothing but K1 plus K2. Okay, this is regarding parallel. See here regarding parallel, please remember same extension. Okay, see regarding this one, same extension. See same extension in the spring, but thing is that the same extension but different restoring forces. And here, see same restoring force, same force is acting on them. But remember, see what is the difference here? Their extensions are different. That is the difference between springs in series and parallel. See here very quickly, see the time period of a spring mass system is what? It is 2 pi root m by k. It does not depend upon the g value. Okay, even if the body is rotating, body is placed in the liquid, body is placed in the inclined plane, the time period doesn't change at all. And the spring constant basically depends upon what? See, it depends upon the length of the spring. It is inversely proportional to length of the spring. That is the second point. And the third point is what? See, the springs in series and parallel. In series, 1 by k is equal to 1 by k1 plus 1 by k2. That is the effective value of k in series. And what is the effective value of k in parallel? That is k1 plus k2 plus. And that means here if there are n springs are there. If there are n springs are there, then see what is the k in parallel? It is k1 plus k2 plus and so on like that. Okay, so here in the next class what I will do, I will be explaining about how to calculate time period in the different cases of the spring mass system. Okay, thank you very much. Okay, this is Vijayam Physics classes. Please kindly watch and subscribe. Thank you.